this lecture is on multi-tenant isolation. So this is like partitioning and network virtualization in cloud data centers. So we are going to talk about 3 technologies actually, I mean 4 here in the list, but really VXLAN, NVGRE and STT, which can all be grouped under NVO3 as those 3 technologies, and they are really used in the cloud data centers today. All right, and by doing this discussion actually by the time we come to the cloud we would have finished all the networking as I said before. All right, so when we go to a cloud and we have multiple tenants, what we want is that each tenant can get complete control over their part of the network. And what does that mean? That means that they can connect by L2, L3 or whatever they want to do. So they want 5 VMs and they want to be connected by whatever method they want to do. It has to be their control. Right? Whatever addresses they want to give, MAC addresses, IP addresses, 192, 172, 10 point whatever, it's their control. Whatever node locations they want to and move around, that's their control, right? So that is what is called partitioning basically, is that network virtualization allows the tenants to feel that they have the complete network under their control. Other tenants in the same data center and the VMs running on the same host can have a totally different address, totally different connectivity, and so on and so forth. Right? Second thing is, it allows providers to serve a large number of tenants without worrying about client networks. So first we saw from the tenant point of view, now we are seeing from the provider point of view. From the provider point of view, they don't have to worry about that this guy is using Ethernet addresses, this guy is using IP addresses, this and that. So that is all, and there are large number of customers. So customers is thousands of customers, right? Location of the individual client nodes, number and values of the client partitions, VLANs, subnets, everything, all the details, those are client's responsibility. And the network could be a single physical interface, a single physical machine, a data center, a metro, or a global internet. So that's another thing, is that when we are talking about virtualization, I think we have already said this before, is that the network definition could be a single card, and that's a network, or it could be lots of machines, or it could be a whole data center, or it could be multiple data centers. Provider could be a system owner, could be an enterprise, a cloud provider, or a carrier. So you know the difference. If I am just a system and I have 2 VMs, I am a provider. On the other hand, I could be a company like Vashu, or I could be a cloud provider like Google or Amazon, or a carrier like AT&T. Okay? So that is what it is. Now, coming back to this chart, which we have presented many times. So today we are going to use this square. We are going to do NVO3, VXLAN, NVGRE, and STT. This is L2 networks using L3. Alex, what is NVO3? NVO3 is an IETF group. IETF group on network virtualization overlays using L3 techniques. Network virtualization overlay using L3 techniques. And so this is a common problem. Data center virtual private network in a multi-tenant data center. So this is basically the problem we talked about, is that you have a cloud and then you want to put many tenants in there. Now it doesn't have to be cloud, it could be simply a company data center in which you have multiple departments which you want to have their own control. So multi-tenant data centers. And the issues are that we want to have very large number of overlays. Scale in the number of networks. So hundreds of thousands of DC VPNs, virtual private networks. These what we call overlays. Right? So there are two words, underlay, overlay. Overlay is what the tenant gets. That's an apartment. Underlay is the whole building that the provider has. Right? That's the high rise. So underlay is the physical network that the provider has, and overlay is the virtual network that the tenant gets, right? So, and we are calling here VPN. In the NVO3 terminology, they call it VPN, Virtual Private Network. So data center virtual private networks, hundreds of thousands of DC VPNs. Scale in the number of nodes. They are talking about millions of VMs or hundreds of thousands of physical servers. Okay? And VM or PM migration. They should be able to move things around. So this is actually the issues that NVO3 is solving. By the way, NVO3 is not done. NVO3 is working right now. And all the protocols that we are going to talk about today, they are not standard yet. They are being used, but they're still being developed. So their goal is to allow migration to support both L2 and L3 VPNs. Some people will want to have L3 connectivity, some people will want to have L2 connectivity, and both are allowed. Dynamic provisioning, anytime you can provision it. Addressing independence. You could use any kind of addressing you want. Again, right now the choices are L2, L3. And then virtual private means other tenant do not see your frames. So virtual private means that if you're living in one apartment, you cannot peek into somebody else's apartment. That means that you cannot see the packets which belong to some other customer, to your competitors. Right? And then optimal forwarding. Optimal forwarding means somehow the packets are not just ping-ponging. Now I don't know whether we discussed VRRP. We discussed it indirectly some time ago. This is the virtual routing protocol, and this was related to the tromboning. That with tromboning the routing is not efficient. You go to the wrong place with other data centers and so on and so forth. But anyway. So these are the things that NVO3 is doing. So the goal is to develop a general architectural framework, identify the key functional blocks, identify alternatives for each functional block. So basically, this is a general problem and there are many solutions. So they said what we will do is they will divide the problem into modules, and for each module people can select different solutions. Deployment can mix and match these alternatives, analyze which requirements are satisfied by different alternatives, and make sure that we can do the management, which means to develop OAM if necessary. Okay? Alright, so they have developed a terminology, tenant system. So whenever there is a tenant system, that is a VM or a PM. A virtual network is L2 or L3 tenant network. NVE, network virtualization as is. Those are the entities that connect tenant systems. So for example, this is an NVE and this is a tenant system, this is a tenant system. So now, if the tenant owns the physical machine, this could be a physical machine. If the tenant owns a virtual machine, then this could be a virtual machine. And whatever connects these two is a NVE. So they are just generalizing the names. Instead of using the switch, calling it a switch, they are calling it NVE. And the reason they have to call it NVE because switch means layer 2, router means layer 3. And here we are developing it for both. Right? So NVE is the entity that connects. Then NVA, Network Virtualization Authority. And so NVA is manages these NVEs. Basically, each tenant has its own NVE and it has its own NVA that somehow manages how to route from one NVE to the next NVE. And then they have NV domain. So this is a domain. So this is what we call an overlay. Okay? This is the set of NVEs under one authority. And then there is a region, which is multiple domains. Alright? So let's just go one more time. This is a virtual network, VN. This dotted thing is virtual network. It consists of many TS, tenant systems, which are connected by NVEs. And when you take many VNs, that becomes a domain, and when you take many domains, that becomes a region. Any questions about that? All right. So underlay network, we already defined that. Underlay network provides the overlay network service, which is basically the physical network. Orchestration systems. So we have already used the word orchestration before. Orchestration systems are the ones that create new VMs and new switches, new network entities. So those are this could be a program or a web page where you go and put something in. And you say, I want 100 VMs connected like this. So that is your orchestration system. NVEs could be in V switches, external P switches, or span both. So NVE is the thing that connects VMs, and that could be a virtual switch, or it could be a physical switch. Or both, just like in WEPA. You use the internal as well as the external. Alright, NVA could be distributed or centralized or replicated. So this is the thing that controls all these NVEs. So that could be a distributed thing, just like OSPF, or it could be centralized, like in SDN, where you have a central controller which has all the routes and tells to all the people. Or it could be and could be replicated. Means if it is centralized, clearly you have to replicate it, so that it doesn't become a single point of failure. Alright, NVEs get information from hypervisors and are NVA. So let's just see this picture that maybe it become clear. NVEs, this NVE gets the information about who is connected to it, how it can find out. It can either use a protocol, or it can just ask the hypervisor there that, okay, you have created 5 this and which is mine, So hypervisor can just tell it right there. Or it could ask the NVA, which is outside right here, outside controller. That is what it says. NVEs get information from hypervisors and are NVA. Hypervisor to NVE protocol, they need some protocol for that, and they need NVE to NVA protocol, and so this is called data plane learning, and this is called control plane learning. All right. So now here's the thing. Actually, what they're doing is they're trying to generalize both L2 and L3, and that's why they have to invent all these new names. And so this is data plane learning is like source learning, and this control plane learning is like exchanging messages. Then map and encap. That is, map and encap is encapsulate. Find destination NVE, which is mapping, and send is encapsulate and send. So suppose you want to talk to some other NVE, you have to find out what their address is, and then send it to them. All right, that is called map and encap. So these are all the special terms that NVO3 has defined. They had a different meaning before when we just said L2. So the problem is NVO3 has actually trying to cover both the links here. Actually, I should clarify that in this we have 2 rows. We have L2 using L3. This is where I put NVO3, but this also covers L3 using L3 right here. They are providing both kind of virtualization, L3 virtualization as well as L2 virtualization. All right. So right now, these technologies already exist. Even before NVO came in, the group came in, we already know BGP and MPLS virtual private networks are used. BGP and MPLS Ethernet virtual private networks are used. VLANs are there, PBB is there, PB is there, so on and so forth. Shortest path bridging is there. VLAN station identifier discovery and configuration protocol. So this was actually QBG. When we were discussing QBG, we had 3 or 4 protocols. BDP was one of them. If you remember, that was the one that was kind of replicating TCP. So that is the one. And then there is address resolution for massive numbers of hosts in data centers. We have not talked about this, ARMD. And if we get time someday, we'll talk about it, but not today. But so there is another protocol. Then Trill, we have talked about L2 VPN, We haven't talked about it, but there are so many L2 VPN technologies. And then proxy mobile IP. Again, mobile IP, we do talk about that in 473. And then there is a proxy mobile IP where you proxy does it for you. And list we have talked about. So anyway, let's see. BGP MPLS. This is widely deployed. MPLS is widely deployed. So we talked about the MPLS part of it. We did not talk about the BGP part of it. Okay? And this is in this table here. Sorry, in the previous table, that my table here. So we have BGP MPLS in this list here. It's not there. But anyway, so there are lots of this layer 3 technologies that we have not talked about. And BGP in particular, actually, since many of you may not have the background, and I didn't want to cover it here, but anyway, so let's see. This is just for historical purposes. These are all old technologies. They exist right now, and they're used right now. So BGP and MPLS is used quite a bit. BGP, MPLS cannot be used in data centers because the hosts do not implement BGP. Right? So how many people know what is BGP? 1, 2, 3. That's it. Yeah, so the BGP is the Border Gateway Protocol, which is the wide area network routing protocol. Just like OSPF is for for small areas, for large areas you use BGP. BGP is used between the enterprises or between the companies. OSPF is used inside the company. So since you guys don't know, I didn't want to go too much into here, but basically since it is used only between the companies, the hosts inside the companies don't know about BGP. They don't know about OSPF. Right, but they don't know much about BGP, and therefore it is not used. It is difficult to use it in the data centers. BGP MPLS is deployed in the carrier networks, but again same reason, BGP is not there in the data centers. 802.1q, PB, PBB, these VLANs are used, of course. Shortest path bridging is being used, and this is coming in. QBG is coming in. So, and so on and so forth. So anyway, so these technologies are there, but they want to develop, they want to see what are the, so one of the things they are doing is, NVO3 group is doing is, analyzing these and seeing what are the things that they don't do that need to be done. And so there are technologies that we'll talk about today, and one of the things that protocol that many of them use is called GRE. So I thought I will put a slide on GRE here first. I think we have discussed GRE before. I don't remember. Did we discuss GRE before? No? Okay. So GRE is generic routing encapsulation. This is pretty old. You see RFC 1701, maybe at least 20 years old. So GRE is generic routing encapsulation. Whenever you want to encapsulate anything into anything, this protocol can be used. This is for anything into anything. All right? So it is generic, X over Y for any X or Y. So over IPv4, GRE packets use a protocol type of 47. So if you have a IPv4 as the delivery header, then it will say protocol type 47, then you know that the next header is GRE. Okay? If outside header. So basically what you take is you take any payload, put the GRE header and then put the delivery header. So this will be, if this payload is let's say X and this is Y, then you will say X over Y. So you could do IPv4 over IPv6 or IPv6 over IPv4. Right? You could do Ethernet over IPv4 or Ethernet over IPv6, or you could do IPv6 over Ethernet. So either one, there are many possibilities there for internal and outer one, right? X over Y, Y over X, X over Y. So this is the thing which is payload. This itself is some technology like IP or Ethernet or IPv4 or IPv6. And then GRE header in the middle, and the delivery header is what it is going on. All right. So if the delivery header is IPv4, then the protocol type field would be 47 to indicate that there is GRE inside it. Optional checksum, loose or strict source routing, and key. Okay, so let's see. First of all, optional checksum. So there is a checksum field in the GRE header to make sure that there is no error in the header. but this is optional. And the reason it is optional is because most often the delivery headers have their own checksum. So if this is an Ethernet packet, Ethernet will have a CRC. If anything happens wrong here, Ethernet will know it first. So anyway, checksum is optional. The next thing is loose or strict source routing. So source routing is again part of 473, and I don't know how many things people have learned or not learned, but maybe I should make a list of all these things, because if people have not learned, they know that they have not done 473. Source routing. Anybody knows what is source routing in IPv4? They never taught you? Dolvara, do you know? Source routing.
Not using the routing table.
Huh?
When the packet is wrong, it's not using the data in the routing table.
Okay.
So
How is it routed then?
it's already known the route in the packet.
Route in the packet. Yeah, that is somewhat correct. Basically what happens is, in the packet you can put the route, you can put in the header itself, you can say go to this router, from that router to that router to that router. That is called source routing. If you put exactly the routers that you need to go, and if they don't find that router, they can throw the packet away. That is called strict routing. Loose means, well, I can say just go from New York to Germany. Now you could go to New York to Germany by many methods, and we don't care how you get there. That is called loose source routing. Alright, so people like us will use loose source routing, but NSA or anybody who has very secure requirement, they will use very strict source routing. They will not want the packet to go any place that they don't want it to go. Right, so that is source routing. Yeah.
Source routing is almost same as MPLS.
So source routing is not the same as MPLS. In MPLS, the path is set up before. In source routing, the path is not set up. It's connectionless. Like key. Key is used to authenticate the source. So you could just put a key here, and that will be for security purposes, right? The recursion control. Number of additional encapsulations allowed. 0 means restricted to a single provider network, and that means end to end. Or you could put non-zero, which means that you could keep encapsulating as many times as you want. Offset points to the next source route field to be used. Now source route is a list, right? Source route is a list, and so you have to find out where we are in that list. And IPsec are commonly used as delivery header. So now this delivery header could be IPsec, secure header, or it could be IP header, unsecure header. Alright. Now GRE is pretty old, and again this is something that 473 people should know. But GRE is, so we are going to use GRE today. So I just put the header here. Now let me see if there is anything in the header that we need to discuss. So we have checksum present bit, routing present bit, key present bit, sequence number present bit. Then we have strict source route, recursion control. Alright, so these are all 1 bit, by the way. Notice first thing. Recursion control is 3 bits. So maximum you could have recursion of 8. Then you have 5-bit flags and 3-bit of version number, 16-bit of protocol type. Now can you guess what is this 16-bit doing here? Protocol type. Can anybody guess what that is for? Yeah. No, that determines what your payload is. You see, every protocol has a protocol type field, which is actually should be called payload type. Right? Ethernet has a protocol type field, that is the payload type. Similarly, IP has a protocol type field, that is the payload type. Here, protocol type field means what is the GRE payload. Alright, this is common. Okay. Offset is basically, as we discussed before, checksum, key, sequence number. Sequence number is basically if you if you have the payload and your source routing list, and this is the source routing list. Sequence number is basically sequence number of this GRE packet. You might have to reassemble or something, fragmentation or reassembly, something like that, with that. Okay. All right. So GRE is done now. So then the next thing we do is we want to do Ethernet over MPLS over GRE. Ethernet over MPLS over GRE. So we will take the Ethernet packets right here. Then we will dig an MPLS tunnel. No, sorry, MPLS. And then we take a GRE tunnel. So you see Ethernet is going over MPLS, and in the middle, in this, we are going to do GRE, and then we are back to MPLS and back to Ethernet. So the packet looks like as follows. Ethernet packet, you take that, you put that inside an MPLS header, means you put the label, etc. You put that MPLS inside a GRE packet. So you put the GRE header, and then you put the IP delivery. So these routers on the way, they don't know MPLS, they don't know Ethernet, and actually, obviously, they don't know anything other than IP. So they just use this IP header to get it from this end to that end. Okay, this header is used to get, external IP header is used to get the packet from the beginning of the tunnel to the end of the tunnel. Alright, this is called Ethernet over MPLS over GRE. Now the question is, why would we use all these different protocols? GRE is required because these guys don't speak MPLS, and we want to have an MPLS link over them. So whenever you want to have a protocol go over something that doesn't speak that language, then you need a tunnel. Remember we said that if you want to send a packet which has an address in English, you want to take it to Japan, you put a Japanese envelope on it, which is called a tunnel. Encapsulation. So these routers don't speak MPLS, and we want to somehow continue our MPLS over them. Okay, so we put a tunnel, and so the MPLS label is there, and this router will say, okay, this according to this label I should send it to that router, and so that is what it is going to do, but except that these guys don't know those label business. So we put a GRE and IP header there in front of it. So now it can go over IP network, and here all those things, headers will be taken out, and then now we can use MPLS header again. Okay. Now with MPLS, you know that we can have many wires inside the MPLS. Remember pseudo wires, and we can have different things that can do with MPLS, and so that's why we need the MPLS in the first place. So you put the Ethernet over MPLS, and then you have a network which does not allow MPLS, so therefore you need over GRE. Well, let's see if we finish everything on this slide. Used when the providers offers only L3 connectivity. Subscribers use their own MPLS over GRE tunnels, and VPLS over GRE or advanced VPLS over GRE can also be used. Now, when we talk about MPLS, at that time we also talked about VPLS. And MPLS is point to point, VPLS was point to multi-point or multi-point to multi-point. Remember, VPLS was the when you try to do a whole, VPLS stands for LAN service, by the way. VPLS, not the label, is a virtual private LAN service, right? So you can have multi-point to multi-point, just like a LAN. So that when, if you want to use that, then you do over GRE. Okay, and then there was an advanced VPLS, which we haven't discussed yet, I think, but that is similar to VPLS. Okay, so GRE offers IPsec encryption option. So in GRE, you have the advantage that you could also use IPsec instead of IP as the outer header. Yeah.
So since between 2 and 3 routers, we will use encapsulation with the IP.
Between 2 and 3 what?
Between 2 MPLS routers, we will encapsulate the packet IP, and why do we need the GRE?
You will encrypt the packet in IP. No, you cannot encrypt the packet in IP. you see, you are saying that you will just use IP and then you will have the payload of MPLS. Yeah, see, the thing is that this is GRE's purpose is exactly that. You want to send MPLS over IP, and therefore whatever is required in terms of fragmentation, reassembly, and everything else on the way is provided by GRE. Okay, so that exactly what we are doing. GRE's purpose is to allow any protocol to run over IP in that sense. Okay. I mean, many of these options, such as that's a good question. Let me think about it. Actually, I'm just thinking that.
So IP does not need to know about any other protocol, and the inside protocol does not need to know about anything other than IP, other than GRE. So GRE is a buffer type of thing.
Yeah, but I mean, so let me think about it. Actually, I think I need to. Right now, what he said is correct. I mean, IP just note that this is a 47 is GRE, but GRE must provide something more than that to just provide a transparent payload. Anyway.
Similarly, in this case, if IPv6 packet has to be sent, usually we use the tunnel of IPv4. But can we simply replace Ethernet by IPv6 packet and use the same encapsulation?
Yeah. So basically, what will happen is, though, if you had IPv6, your MPLS might be MPLS 6 or something. I don't know, there is an MPLS 6.
Sometimes they give dual stacks.
Yeah.
But then, if that is not possible, you have to send IPv6 and a tunnel of IPv4.
Yeah, then you will use GRE.
Then GRE, I mean, same.
Yeah, so if you forget the MPLS, then if you had IPv6 here, then you will use GRE to send over IPv4. Okay, all right. So the first protocol then we use with GRE is NVGRE, network virtualization over basically using GRE, and that is Ethernet over GRE over IP. So basically we got rid of MPLS. So we have Ethernet which goes over GRE, Ethernet over GRE over IP. All right. A unique 24-bit virtual subnet identifier is used in the key field. So 2^24 tenants can share this tunnel. So you remember there was a key field there before, and that key field is 24-bit long. So you can have every if there are multiple tenants sharing that tunnel, then you can take them out here and then put them into the right direction to give it to the right tenant. Unique IP multicast address is used for BUM traffic, and so you know BUM traffic now very well, right? BUM is broadcast, unknown, and multicast, which means that it has to be given to everybody, or at least to some people, more than one person. So for that you have to use IP multicast. Yeah.
Is used sense for unknown or unicast?
Broadcast, unknown, and multicast. Yeah, I'm sorry, what did you say?
We have it in a previous lecture. U is for unicast.
U is for?
Unicast.
No.
We have it.
Unknown unicast. Oh, no, hold on. Let me correct that clearly. When we say BUM means broadcast, unknown unicast, as well as multicast. The reason unknown unicast, what do you do with the unknown unicast in Ethernet? You have to broadcast it. See, if you get an address, if you get a packet you don't know where it is, then you just send it everywhere you can. So unknown is done the same way as broadcast.
I checked it like the previous slide.
Yeah.
You mentioned like broadcast, unicast, multicast. And the qualm you said.
No, okay. Correct that one. What is the slide number? Can you give me a pencil? Huh? Yeah, just correct that to unknown. Yeah, unicast is actually, if it is not unknown, then unicast is sent only one way. Only unknown unicast will be sent like a broadcast, and multicast is another one. Is that multicast? Suppose it is going with 5 people. Now, some places they will figure out who 5 people are, otherwise they will just send it to everybody, and those 5 people will pick up, other people will not pick up. So the multicast is also transmitted on the Ethernet just like a broadcast. Okay, and unicast is transmitted like a not unicast. Unknown is transmitted like a broadcast. So bump traffic. All right, VSID. VSID is virtual subnet identifier. That tells you who the tenant is. Equal cast multipath is allowed on point-to-point tunnels. So basically what it is saying is that when you have this tunnel, it looks like one wire, but it could be 2 wires. Equal cast multipath. Anyway, this is not a wire because this is not a connection or anything like that. And so the packets could go any way you want, but the idea here is that the packets do not have to follow the same path. They could be multipath. Any question about NVGRE? And there is another mistake here. I think it says MVGRE. It should be NVGRE in the reference. Not that it makes any difference.
This point-to-point tunnels, which would mean between 2 edge switches.
Yeah, so the thing is, here the thing, the point-to-point tunnel is connectionless. So the path is not given.
Yeah, so when we make multiple path involves like multiple for when they'll be sharing load or they'll be increasing the capacity of the link.
Right. So when you use multipath, you are basically increasing the capacity, right? Because instead of if everybody took the one path, then you will have half the capacity. And multipath doesn't mean 2 paths. Multipath could be 4 paths, right? Equal cast paths. See, basically what they do is they don't take, if there are 2 paths, one is short, one is long, then they don't divide anything. Everybody takes the shortest path. If there are multiple shortest path, then they divide. Okay? And that's why they have that sequence number. See, that is one thing that GRE provides, is that sequence number. And that sequence number will help you put the packets in the right order before you send them off. So the edge device will see the sequence number and say, okay, this is sequence number 4, 5, 6, 7, whatever. The sequence number was in the header, right? Sequence number here. That will help it put it in the right place. Okay? NVGRE. So now we are doing Ethernet directly over GRE. Previously we did it over MPLS. So here is an example of how NVGRE could be used. So this is a data center where the provider has 3 subnets. And the first subnet is 192.168.1x, second subnet is 168.2x, and third subnet is 168.3x. And the tenants have their own subnets. The first tenant wants to label its tenant numbers by 10, 22, 1, 22, 3, 4, 5, like that. So the first tenant wants to have the subnet labeled as 1022x. Second tenant wants to label it as 1021x. Just coincidence that both want to use 10. They could use 172, one could use 172, one could use. So now you see, this is a subnet which is tenant subnet, and this is a provider subnet. They are all very different, but on the same machines. Okay, and this is what NVO3 wants to do, is that the tenants could select whatever they want, and the provider could do not have to worry about whatever the tenants are using. And that's why when you use this GRE encapsulation, you don't look inside what is there. All right. So this GRE helps because we don't look inside. It could be IP packet here, and we don't look inside whether it is 10 or whatever it is. It's the outer one which takes you to the destination, right? So the outer one will be these ones. Inside, the customer could be using those ones. Okay, that's why we need GRE. Is to hide the inside information, put it inside another packet, and send it over the subnet.
Actually, the requirement of GRE came because when we were implementing protocol stacks, for example, if I'm implementing MPLS stack, if I'm implementing IP stack, I don't need to know, when I'm implementing IP, I do not need to know that I can sometimes run over MPLS. When implementing MPLS, I do not need to know, sometimes I will run over IP, IPv6, whatever, right? So I put a middle thing in between GRE, which is like an abstraction. So that guy knows, okay, I have IP on this side, MPLS on this side. Layer 2 on this side, layer 3 on this side, whatever, on two different sides, and that guy implements whatever, and you can just implement your specific protocol as it is. The kernel endpoints are fixed. The GRE takes out the kernel endpoints. You don't need to care about what type of kernel you are setting up while implementing. See, so IP will implement only IP, MPLS guys will implement only MPLS, and not care about anything. The GRE guy will just implement the whatever requires to do the matching between the two endpoints. It's easy to implement when you have something in the middle to allow anything over anything else. Otherwise, you have to implement everything, have a connection with everything else. So the IP will have to be ready for protocol types of TCP, UDP.
Okay, so let me summarize what you said. Let me just say, if you have n protocols over m protocols, okay, you will need n times m protocol types. Let me give an example. If you have two protocols, let's say Ethernet and IPv4 over two protocols, maybe IPv6 and MPLS, whatever, right? So you need protocol types field to go into the outer header to say what is inside. So you will need n times m, which is like n squared protocol types. With GRE, you have only one protocol type for GRE in every protocol, and then you have one protocol type for every payload. So you have only 2n protocol types. Is that what you are saying?
Yeah, and implementation. So when somebody is implementing IP stack, actual C implementation, for example,
Yeah.
he doesn't have to care about that my packet can come with an MPLS inside it, or it can come with TCP inside or UDP inside it. He just knows that whenever it comes, it will have something which I know. It just comes with GRE inside it. So when I'm implementing, I do not expect many different type of packets. That is taken care of by GRE. The mapping between two different protocol types taken care of by GRE. The kernel endpoints are similar. It's not two different kernel endpoints. One type of implementation. So I can just implement IP and forget about anything. GRE will take care of IP over MPLS or IP over something or IP over X, Y, Z, whatever, and put it there. I don't need to take care of that. It's like, the operating system takes care of all the different type of drivers, the device drivers. The application does not take care of, okay, right, let's create an application for this particular sound driver or that particular sound driver.
I have to think about that. And so the reason I have to think about that is because these guys don't have to worry about any of that. They are just using IP headers.
Yeah.
You only the endpoints. Now the endpoint has to basically, whether it is GRE or not GRE, has to know Ethernet.
No, it has to be Ethernet. There will be Ethernet implementation and there will be an IP implementation. GRE implementation matches this both. Even endpoint, there are different guys implementing different stuff, right?
Yeah.
Ethernet is implemented by different group of people.
Okay.
And
So I take your word for it. I mean,
so
like
when you design a new protocol, you just put a driver to the GRE.
for GRE.
Implementation.
Yeah. Okay, so let me say what he said. He says that these two routers, the end routers, right here, the last router and the first router, they have to implement something. other than IP. Right? The middle router only implements IP. But the tunnel endpoints have to implement something. Now they could be implementing many different things. Instead of that, they said just implement one thing, which is GRE, and we're done with it. So then GRE handles everything else. That is his point. And I think that, that makes sense, is that the tunnel endpoints only implement GRE, and inside GRE everything else is handled. So that's a kind of a standard way to handle any protocol, rather than these tunnel endpoints then worrying about Ethernet and other things. Okay, did I say it correct, what you said? All right, I think NVGRE is there. Let me just see if I can do more. Okay, so I think this one we did is that, so now you see clearly, I don't know whether it makes sense or not, that the tenants can have a totally different subnet numbering than the providers. Okay, this is a tenant dotted line, this is a tenant dotted line, these are VMs dotted line, right? And this is a solid line, is a provider physical network. So when the packet is going from 10.20.1 to 10.20.2.5, it will be encapsulated into GRE, and these outer headers will be like this, 1960 whatever 192 numbers, and they will find their way here to this physical machine, and then it will go there. Yeah.
In your example, would it be safe to say that there are actually two GRE tunnels, one between the VMs and the edge router of the provider, and one between the provider and the other provider?
No, okay, this is all one provider, by the way. I'm sorry. These are three physical machines. Okay, let me say. This is one physical machine, this is second physical machine, this is third physical machine. Okay, this is all one provider. So the tunnel will go from this machine to this machine. Tunnel will go from this machine to that machine. So, you could have one tunnel, two tunnel, and three tunnels maybe. Okay. All right, I think this would be a good time to take a break. So the exam will cover everything up to here. Up to NVGRE and GRE.
You mean after the return?
Monday exam, huh?
Monday exam, after last exam.
From the last exam, whatever we cover up to we didn't cover in the last exam, that point onwards to this slide, 1313.